Hello, welcome to Basics of Finite Element Analysis. Today is the fifth day of this week, and what we are going to discuss today is a radially symmetric problem. So, till so far whatever problems which we had been doing were using a Cartesian frame of reference, but today we will actually do again a boundary value problem of second order, but here we will use a cylindrical coordinate system. Examples of such problem could be that suppose you have a very long pipe and some hot fluid is passing through, and what you are interested in knowing is that how is temperature changing in the radial direction. If the material properties of this pipe are radially symmetric, and also if the cross section of the pipe is uniform and radially symmetric, even though and it also does not change in the z direction, then we can reduce this 3-dimensional problem to a 1-dimensional problem. So, in general, for several types of such types of problems, the governing equation could be written something like this. And this governing equation is valid for values of r which are larger than internal radius of, it could be 0 or non-zero entity, and an external radius. So, the first step in this whole process, if we have to develop its K matrix, is to develop a integral formulation for the whole thing. So, 0 equals W times minus 1 over R d over dr and at this stage we have to realize that we are integrating it over the whole volume of the system. Okay. So, suppose this is my cross section and I am looking at a small element of this, right. So, that is my Ri. The location of this element is R, the thickness of this element is dr, and the length of this element is r d theta. So, then the volume of an element will be, so this I will be integrating it with respect to volume, and this dV is equal to r times d theta times dr, which is the area of this cross section small element, and then in the z direction it is dz. Also, when I, so this is a volume integral, and also the limits of this volume integral will be, when I am integrating on theta, it will be from 0 to 2 pi. When I am integrating on z, in this case I assume that the length of this pipe or cylindrical cross section is 1. So, just for simplicity purpose, that is the only reason. But if it is L, then I can make it 0 to L. So, so when I integrate in for on z, the limits will be 0 to 1, because dV is having d theta, dr and dz. So, I will have 3 successive integrals, and when I am integrating it on r, I am discretizing this whole radius Ri minus into small elements. Okay. So, it will be from R A to R B. So, my weighted integral is basically three integrals W of minus 1 by R d by dr A u prime minus q, and then the first thing I am integrating it is with respect to R dr. So, I am replacing this dV by this entire thing, then I am integrating it with respect to theta, then with respect to z. So, my limits are Ra to Rb, 0 to 2 pi and 0 to 1. Okay. I have this extra R term because of this geometry, and this is how the cylindrical geometry, which is radially symmetric, when we do this weak formulation, this extra R term comes. If we had done for a Cartesian system, it would have been just dx times dy times dz. So, there is extra dimension does not come, but here we have this thing. So, that is why I wanted to cover this, that for a cylindrical system which is radially symmetric, we have this type of a problem or formulation. So, once I integrate it from on z, all the parameters in the parenthesis are independent of z and theta. So, this dz is just goes away, right. If it was 0 to L, then it would have been replaced by L. Okay. Same thing with theta. So, this goes away and I get a 2 pi here. So, this is equal to 2 pi Ra to Rb W, and I multiply R to the terms inside the bracket. So, I get this R cancels. So, I get minus d over dr A u prime minus q r dr. At this stage, I do my weak formulation. So, I shift and so I shift the differentiability operator from this A u prime to W. Okay. So, what I get is 2 pi Ra to Rb W prime A u prime minus W q r dr minus, I get some boundary terms, W times 2 pi A u prime evaluated at Ra and Rb, and this, so I get the same expression here, and on the boundary term I get W evaluated at Ra times Q1 E plus W evaluated at Rb times Q2 E, where Q1 E equals minus 2 pi A u prime evaluated at Ra and Q2 E equals plus 2 pi A u prime evaluated Rb. So, that is my weak formulation. So, now I have to, at this stage, I assume some interpolation functions, and what I will do is I will assume and using those interpolation functions I can construct the K and the F and all these matrices. Okay. So, at this stage I assume that U for the eth element is equal to right and W is equal to psi I, where psi I is equal to psi I, it is a function of R. So, using this I get 0 equals 2 pi integral from R A to R B d psi I over R A d psi j over d R times U j of E. I am summing it up over j. So, this is one term dr minus R A to R B 2 pi psi I q r dr minus these terms in brackets. Okay. Or what I can do is I can remove 0 from here and I can put an equal sign here and this becomes a positive sign. And of course, this is for the eth element. So, at the end of the day I get a K matrix times a U vector is equal to a force vector plus a Q vector all at element level. And what is the definition of psi 1 and psi 2? So, psi 1 of R is equal to R B minus R divided by H E and psi 2 of R is equal to R minus R A divided by H E. Or if I want I can go to local coordinate system and change these things. And finally, K I j for the eth element equals 2 pi A d psi I over dr d psi j over dr. If you integrate it from R A to R B dr for the eth element, and your F for the eth element equals 2 pi integral R A to R B psi I E times Q R dr. So, if you have this formulation, then you can solve a lot of problems which are practical problems. Suppose there is current flowing in a wire or in a heavy conductor and it is generating heat, and how is that heat getting dissipated through the insulating mechanism. And these type of problems becomes really important when there are big fat conductors running in the ground and you want to see how is your insulation going to deteriorate over a period of time, or flow of a fluid or a diffusion in a radial direction. So, all these types of problems can be addressed using this formulation approach. For the linear element, that is an element which is linear in the radial direction, Okay. So, we have to remember that Ke equals 2 pi Ae over He times Ra plus He over 2, 1 minus 1 minus 1 1. So, that is the definition of the K matrix, and the definition of E matrix vector for the eth element is 2 pi Qe He over 6 times a vector 3 Re plus He and 3 Re plus He. Okay. So, what is R here? It is the actual position of that radius. So, this I just wanted you to look at it, excuse me. So, this is actually not E, this is Ra. So, the stiffness matrix properties in this case, they change as I move out or move in, they are dependent on Ra. Okay. So, this is what I wanted to discuss in context of radially symmetric problems for cylindrical coordinate systems, and you can use this formulation to address some of your needs. This is also a one dimensional problem, but its formulation requires a little different approach, because here you just do not integrate it with respect to dx, dy, dz. Rather, the definition of dv is r d theta times dr times dz. So, in the formulation things become slightly different. So, this is what I wanted to discuss today in context of radially symmetric problems. Thank you very much, and we will continue our discussion in the next class. Bye.